Hi there, friends and neighbors. I'm going to show you a complete example of a multiple regression results section. We're going to kind of keep it light because this is a relatively introductory class. All results sections, your typical results section is going to have descriptive stats, graph, and inferential stats. So I'm going to just go ahead and dive right in for that. The null hypothesis for regression has to do with the beta weights. So we're saying HO, beta whatever, beta 1 equals 0, that there is no effect of that constant. That constant is 0, so whatever variable that's tied to has no relationship to the outcome. H1, beta 1 is not equal to 0. HO, beta, let's say 2 equals 0, and H1, beta 2 does not equal 0. And so on. We do this for each of them separately. And you pick your alpha, which can be anything you want as long as it is 0.05. Okay. Descriptive stats is going to be means, standard deviations, sample sizes, and the correlation matrix would be nice also. Now what I've got here is just a questionnaire I use on the first day of my stats class. Go statistical analysis, continuous variables, and we'll do linear regression. I don't know what I want to predict. Let's predict how tall you are up to your navel. And we'll use your height, your total height, and your nose length as our two predictors, height and nose. Hold down on Control to choose multiples. Let's show basic diagnostic plots, even though we probably won't really understand them. Then I'm going to click OK. And here are the diagnostic plots. Suffice to say this looks terrible. This is our check of normality. We can see that the dots tend to stay far below the line on the left side and far above the line on the right. It's not good. We want them to be pretty much on the line. So we violate normality. This shows that it's very wide in the middle. We violate the homogeneity of variance assumption. This shows a great deal of influence on the outside, so we violate the independence assumption. We've got some outliers and extreme values. Oh wait, actually residual versus leverage shows you influence as well. Cook's distance is a measure of that. Anyway, this is bad. Bad scene, Charlie Brown. I'm going to copy it. Print screen. Copy to clipboard. I didn't expect that we would meet the assumptions. I just want to show you how to run one of these things. And so, tool selection. If you've got a Windows or Linux, Windows or Mac computer, you can just right-click and copy the image. But I'm doing something different, so this is how mine works. I'm going to paste the graph here. Right-click. Anchor as character. Make it smaller. Cut. And paste it. Okay, there we go. So as we can see, this is a pretty bad graph. So the assumption check, we assume, we have a lot of assumptions for multiple regression. Normality of the outcome. Not met. You can tell it's not met because this graph shows dots clumping below and clumping above the line. That's bad. Independence. We want the input variables to not be too strongly correlated. We want, let's see, homogeneity of variance. We want no influential points or outliers, but that's met with the normality assumption. Let's see, we want to avoid, want the matrix to be invertible, so we want the correlation of the input variables to not be too strong. If they are, that's called singularity. No, what do you call it if it's not completely singular? Well, let's just say singularity. We want the correlations of inputs to not be too strong. Okay, it's a multicollinearity, that's what it's called. No multicollinearity or singularity. Okay. And what's the other assumption? Let's see, normality, independence. Oh, independence. which you achieve by a simple random sample. Normality, independence, linearity. Oh, linearity. Okay. That makes a line, not some other kind of shape. But anyway, we don't really meet any of the assumptions. This is terrible. It's just an example for class project. Okay, so let's get our descriptive stats. That's the means and standard deviations. And correlations would be nice as well. Discard changes. Go to our R window. Statistical analysis, continuous variables, numerical summaries. I'm going to get for height, navel, and nose. I'll get all the descriptive stats. Click OK. Copy the whole thing. Right click, copy. Go back to my word processor, paste. Select it all, and make it look pretty. There we go. All right. And the correlation matrix would be good here too, but I don't feel like doing that. Let's run our regression analysis. Okay, I think I might have already run it. I did, in fact. And here it is. Oh, VIF, the variance inflation factor, that's something that you use to see if you violate the assumption of multicollinearity, too strong of a correlation among the variables. This is a test of whether there are significant residuals, which tells you if your model is incomplete. But let's focus on the ANOVA summary table, this part here. Actually, this is worth looking at. The residuals, minimum of -23 and maximum of 26. Those are huge residuals to have. It's not good at all. Copy. Paste. Select it. And make it Courier. So it looks pretty. All right. So here are your regression constants. There's the intercept. Here's B1, the weight associated with height. It is statistically significant with a wee tiny p-value. Here is the weight, the B2, associated with nose, and it is not significant. So what we see here is that height is significantly predictive of navel, and nose is not significantly predictive of navel. The overall model has an R squared of 0.667, which is very strong, or 666, which is very strong. P-value is way less than 0.05. It's definitely significant. And that's kind of what we would say. So the overall model is strong because height is a significant of navel. But nose is not a significant predictor, because the p-value is greater than alpha. I think that counts as the interpretation as well. Height predicts navel, but nose does not. I should say positively, because it's a positive. You see, it's bigger than 0. It's positive 0.746. Okay, that's a complete example of a results section. It'd be nice to also have the correlation matrix, but I don't want to get too fancy right now. All right.